Okay, so I'm going to talk a little bit about NVMe over fabrics and the work we've done over the last year, primarily, to get this to scale up. So over the last year, we have done a significant amount of redesign on NVMe over fabrics target to change the threading model to improve the way it scales in a couple of ways. Okay, so the agenda is going to be, I'm going to try to do the first 15 minutes of design overview of the new design, then the second 15 minutes of benchmarking, particularly as you scale the number of connections and as you scale the number of CPU cores. I was considering showing how it scales with the number of SSDs, but we've shown that slide a whole bunch of times, and it's linear. The design overview part is going to be a lot because it's a whole new design of an NVMe over fabrics target, and I'm going to try to do it in 15 minutes. So I'm going to talk quickly. I drank a bunch of coffee. I'm going to talk about a lot of concepts about concurrency and message passing and things like that we use in SPDK. If you need to decipher what I'm saying, it might help. There's a documentation page, spdk.io/doc, and there's a concept section that's near and dear to my heart. I've spent a lot of time on those documents. There's one in there called Message Passing and Concurrency, and that will sort of enlighten a lot of what I'm saying, I think. So let's go. Okay, so the NVMe over fabrics target is first composed into two parts. One is an application. That's mostly an example of how to use it. The other part is a library. I'm almost entirely talking about the library here, although the benchmarks will be the application. The application is just using the library to make it a target. The library exposes three top-level primitives that you get to manipulate. One is an NVMe target. That's the top-level thing. That contains, at the highest level, subsystems and transports. So it can contain NVMe subsystems. That's a concept from the NVMe over fabric specification. We'll go into what those are in a minute. The transports are also defined by the NVMe over fabric specification. There are two with three on the way, a third on the way, that are defined, RDMA, Fibre channel, and TCP/IP. SPDK today ships with an RDMA transport. We will work on a TCP transport at some point. And then it was excellent timing. I saw the article that NetApp has now shipping a product that contains SPDK NVMe over fabrics target with a Fibre channel transport with Broadcom, yes. So hopefully we see that upstreamed soon. So it's exciting. We're going to do all three transports, I believe. What's important about these objects are that they are global in scope. And by that, I mean the data structure that represents them lives in a place in memory that all threads can access. So the way you change them is actually a complex set of rules. We don't take locks. That I'll cover in just a moment. Okay, so a subsystem is itself a collection of NVMe controllers and NVMe namespaces. So a subsystem is a global thing in memory. It has a state machine in it, and it's in various states. It is read-only in the active state, so all the threads can read from it. But it is, you can control the state machine to kick it into other states so that you can mutate it at runtime. Controllers in NVMe over fabrics, this is a little hard to initially grasp, but those are effectively network sessions in NVMe over fabrics. Controllers come and go in response to new admin queue connections. So they're not real things like on a real NVMe device. Namespaces map one-to-one to block devices in the SPDK BDEV layer. Those are persistent things. You can do reads and writes from them. There are n controllers and n namespaces. Any controller can see any namespace. That's by spec. Okay. So in addition to the 3 top-level global primitives, there are another set of things in SPDK called poll groups. And this is really what's new in the last year. The poll group is a set of objects that have per thread scope. So you create a poll group on a thread, and then you can only use it from that thread forever. And you can create n poll groups. 1 per thread is the typical model. This contains transport poll groups and subsystem poll groups, which will show what those contain. These are effectively per thread caches of data mirrored out of the global equivalent object, so that you can reference your per thread cache of that to avoid taking locks. Okay, so the transport poll group, which we just saw was inside the poll group, is a collection of NVMe Fabric's Q pairs. This is the part that is important for scaling connections. An NVMe Fabric's Q pair is defined as, for an RDMA queue, it's an RDMA Q pair. For a fiber channel transport, it's a fiber channel connection on a particular hardware Q pair. For TCP, it's a socket. It's 1 connection. This grouping of NVMe Fabric's Q pairs on a poll group are all placed into some thing that can be polled as a unit. So most of these transports have some way to poll a set of things in a more efficient way than polling 1 thing. For RDMA, that means all of these RDMA Q pairs share an RDMA completion queue. For fiber channel, that means they're all in the same hardware Q pair. And for TCP, that's usually ePoll or KQ. These Q pairs, beyond sharing this mechanism for efficient polling, are not otherwise related to one another. They're not necessarily for the same subsystem. They're not for the same controller. They're only grouped in how you can poll them efficiently. And we'll go into why that is in a moment. The subsystem poll group, similarly, contains a collection of I/O channels. So to submit an I/O to a SPDK block device, you must have an I/O channel that is for the thread you're submitting it from. So every thread, remember, every controller can see every namespace. So any Q pair on any thread for a controller has to be able to submit an I/O to any namespace in the back end. That means it needs a per thread I/O channel per namespace. So that's what's contained here. This is, again, so that we don't have to look up global data when we handle a connection. A connection can run to completion on a single thread and has all the data cached in that thread for the whole I/O path. Okay, so here's a little overview of what happens when a new connection arrives in NVMe Fabrics. SPDK defines a top-level function called accept. It's on the target. And you tell the target, you periodically poll the target, say, accept new connections. You can do this from any thread. And one of the parameters to that function is a function pointer that you give it. And that function pointer will be called every time it finds a new connection within the scope of calling accept. So it's not like permanently registered. You just call accept and it calls your function n times for however many connections there are, and then it's done. And in this callback, it's going to give you a pointer to a partially initialized NVMe over Fabric's Q pair, the new connection that it found. So again, an NVMe over Fabric's Q pair is, for RDMA, an RDMA Q pair. For TCP, it's a socket. Your job in that callback is to assign it to a poll group. And the connection is not live until you assign it to the poll group, because it doesn't have an associated completion queue for RDMA, for instance. To do this, you're going to have to pass a message, probably, to the right poll group. And it doesn't really matter what poll group you pick. That's part of the application's decision. The SPDK NVMe-oF target application just does round robin. although we have some ideas for load balancing style algorithms and things like that. But it's simple right now. It just round robin assigns them out. So one of the real challenges here is if you want to do a better algorithm than round robin, you have to decide what do you know about the connection when you need to make this decision. Because with a socket and epoll, you can later remove it from the epoll group, change it to another thread, and re-add it to a different one. But for RDMA and Fibre channel, that's not the case. When you select the completion queue for RDMA, it's done. You can never change it again. So effectively, when you choose the first poll group for that connection, you can't move it. So you want to do that assignment intelligently. So what do you know about the queue pair? Well, the answer is basically nothing. The spec, the way the protocol works in the spec is it doesn't tell you what subsystem it's for or what controller within that subsystem it's for until the first message. But I can't receive the first message until I pick the completion queue, right? So this is why it just says round robin. There are a couple of things you know. You know what IP and port it came in on. You know the state of the whole system in terms of other connections, so you can like load balance. You could assign it to the poll group with the fewest number of connections or the least busy connections or something. But that's basically it. So originally, last year, SPDK used a strategy where we tried to group all the connections for the same subsystem onto one core. And that doesn't work with this shared completion queue model for this reason. So what we did before was we just create a completion queue for every connection, just make a new one. But then it's inefficient to pull them because now you have to iterate the list of completion queues for every connection you have in the system. And if you have 10,000 connections, you're doing 10,000 poll calls instead of one. So we moved to this new model. Okay, and then we'll just, this is the last slide of the design overview here. Then we're going to go to talk about some benchmarks, and I'll take some questions after that. So a little bit about performing an I/O, and this is not going to go into enough detail for you to entirely understand how this works, but hopefully it gets you interested. So when we perform an I/O, we take no locks, the entire data path, all the way down to the device. We tend to touch only thread local data. So it's very cache friendly. So the data we're looking at is only accessed by our thread, so it stays in our CPU's cache. And all the lookups are array math. There's no complicated data structures here. Okay, so what happens is on one thread, it's a poll group, it's spinning. So it starts off and says poll, check for incoming requests on my set of connections, which is for RDMA is look at the completion queue, see if it's indicating that there's any outstanding commands coming in, if I've got any received completions effectively. Once we get a new command coming in, we parse the command. It's an NVMe Fabrics capsule, 64 bytes, which is effectively an NVMe command. We figure out what this command wants us to do. We know what queue pair the command was coming in on, and so after the first message on that queue pair, we now know what subsystem it's for and what controller it's part of. And so we've cached that. And so once we've parsed it, we do a lookup and we say, okay, what subsystem, controller, namespace is this command targeting? Then the next thing we really want to be able to do is submit the I/O to the BDEV layer in SPDK, which means I need to look up the correct I/O channel to use. So I look in the subsystem poll group, and I have that nice array of I/O channels. And it happens that the index into that array is the namespace ID. So I do a little bit of array math, grab the pointer to the channel, submit it to the BDEV behind the scenes using that I/O channel. And then we do it again, right? And it just keeps doing this. So that's the whole thing. All right, so now we can go to the fun part. So the first one is the least interesting. But a little bit about the setup here. I have two systems sitting 6 inches apart. Each has two 50 gig, or two dual port 50 gig RDMA NICs, so 200 gigabit total networking bandwidth. Each port on the systems are directly connected, so there's 4 cables going across for the 4 ports. For the first few, I'm just going to use one of those ports, so 50 gig. The last one I'll use 200. I'm always using a RAM disk here in SPDK. That's one of the types of BDEVs we provide in Malloc disk. Using a real NVMe device doesn't have a material impact on these results. It's just I would need more of them to saturate 50 gig or 200 gig Ethernet than I need with RAM, so it's just convenient. So what I'm showing here is 4K IOPS, doing random reads, queued up 32, and I'm just going from one connection up to 16. And the initiator side, which is SPDK, is limited to 1 core, and the target is limited to 1 core. So all these connections are getting processed on the same core. There's 1 pole group on the target. So I can see even with 1 connection, I can saturate 50 gig. Right, it's not a problem. That 1.2, 1.3-ish million 4K random reads is saturating a 50 gig Ethernet connection with RDMA. And as I scale up, there is slight overhead. It's like it does dip a little bit. Because now it's the effective queue depth is, on the far right side is 16 times 32. So there's slight overhead there. I think this is actually probably a CPU caching effect more than anything. As you iterate over larger sets of things, they blow out your CPU cache. It's not as hot. It could be something else. I'll investigate further. But it's mostly flat, right? Like, we're not CPU bound here at all, and 50 gig is fully saturated. All right, and then the next one is scaling up the number of idle connections. So if I were to have done this test last year, you would have seen a slope on the SPDK NVMe-oF target. So the more idle connections you spin up, the slower active connections would get, right, which was a real problem. So again, this is the same hardware setup, 1 core on the initiator, 1 core on the target. And I have 1 active connection doing 32 queued up of 4K random reads for every single data point here. It's just 1 connection running. The different data points are how many other connections are present on the system doing nothing, right? And so before, we used to create like a single RDMA completion queue per connection. And so now it would have before gone from polling 1 active connection to 513 on the right. And that would have really severely hurt the performance. You actually see pretty clear drops at the size of your L2 cache. So as soon as the size of the registers or the memory you have to pull, times number of queue depths exceeds the size of the L2 cache, you see it immediately drop because now it's thrashing your L2. And again, if you got big enough, you would see it drop at the size of L3. Now you see there's absolutely no effect, and that's because we're sharing RDMA completion queues. So I'm just pulling the same piece of memory for every queue, no matter how many there are. Okay, and so this is a chart showing memory usage versus number of connections. And it's perfectly linear, and the slope is very slow. So basically, every time you allocate a new connection, we have to allocate a queue depth worth of 64-byte commands and a queue depth worth of 16-byte completions. We pool the data buffers in our design, so that is a constant. It doesn't go up or down. It's configurable. If you were to turn on in-capsule data, which means you can send actual data along with the write command, then that would impact the slope here because we'd also allocate a buffer per, a data buffer per I/O, or per command, per queue. We so far find this scaling, going up to 5 or 12 connections, you're using 80. This is a additional memory consumed above and beyond the, the baseline system. So, if I add one connection, it adds like a couple kilobytes. And then as I go to 512 connections, it's using 80 megabytes more than no connections. We find this scaling pretty good. You're going to get to a very large number of connections before memory is an issue. If there ever is a case where we need to be at, I mean, it would have to be a lot of connections for this to be a problem, but if you needed to use in-capsule data with 10,000 connections, there are things that could be done here that I would be happy to talk about on the mailing list or tomorrow at the Developer Summit. So far, it doesn't look like that's necessary, but we are willing to entertain some of that. Okay, and then my last chart here, before I go to questions, is performance versus number of CPU cores. So I have the same setup again. I have the 450 gig ports direct connected to each other. The initiator in this setup is, so I've created 4 subsystems on the target. Each subsystem has 1 malloc disk. I've got 4 initiators running on the initiator side, 1 on each core. So the initiators are always dedicated cores because I'm not benchmarking those. Each initiator is using 1 of the links, basically. So they have 50 gig of bandwidth available to them. The target then, I say, run all 4 subsystems on 1 core, run, half on, split them into 2 cores, split them into 3 cores, and then give them 1 on each is the final bar. So you can see here, as I add CPU cores, it just scales linearly. And that's because we're not taking any locks. Everything is independent. But basically, 1 core can do about 50 gig worth of RDMA network transfers. 2 cores can do, 2 million 4K IOPS, a little more. 3 cores is a little more than that, a little more than 3, and 4 cores is 4.25 or something, which is about where the NIC is capping out. So perfectly linear scaling as you go. All right, and then I'm ready for questions.
Did you enable hyperthreading for your performance tests?
Sorry, what was that?
Did you enable hyperthreading?
Yes.
Does it help?
So it's just like adding more CPU cores, effectively. Now, the way that the CPU cores are sharing the cache is a little bit different, right? So it's not the same as adding a whole new core, but it's mostly the same. It doesn't, we're pinning our threads to cores, so if you pin them to 2, V cores on the same physical core, you'll see drop-offs as you expand the cache sooner, right? Because they're sharing the underlying cache. But otherwise, it doesn't really matter.
Do you have any estimations of what percentage improvement you get with the scaler?
I don't have the numbers for how much. If you're running 2 threads that are V cores in the same shared core, I don't know how much as a percentage that is going to impact your total. SPDK is, the 2 things running on those V cores are not related to one another, basically. So whatever general impact hyperthreading has is going to be the same.
So I have a couple of questions. The first question is, could you elaborate a little bit about your memory advertisement strategy for RDMA?
Our memory?
Memory advertisement strategy between the 2 endpoints of a connection. Like, as your packet size increases, other than 4K, as you go towards 1 MB or 2 MB payload sizes, how does your performance look like with NVMe over target implementation with RDMA? So that is...
So today the data buffers are all allocated in a single global pool. To pull data buffers out of that pool it requires an atomic operation, but not a lock. The buffer sizes are the max. You get to configure what your max I/O size is, but we just basically allocate max I/O size buffers for everything because they're pooled anyway. So it doesn't really, and then when you connect to an NVMe or Fabrics controller, it tells you the maximum data transfer size, just like an NVMe or controller would. So we just tell you what the maximum data transfer size is, and if you need to do a bigger I/O than that, you have to split it on the client. That's the same for an NVMe device. It tells you its max size, and if you need to do I/O larger than that, you split it. There are things we could do to improve that certainly have been discussed. We only support one scatter-gather list element coming over the network today because, again, our buffers are max I/O size. If that buffer pool was a set of 4K buffers instead, then we could DMA to a list of 4K buffers that adds up to your current I/O size. That would be a more efficient use of memory. And it would add processing overhead because now instead of a pointer and a length, you have to iterate the list everywhere you're trying to touch the memory. I don't know how much of an impact that would be. I expect it to be small. It would just make the code more complex. But I think we probably will move that direction.
Okay. So the second question I have is, how do you decide how many connections form into a pole group? So is that tunable static, or is that something dynamic that you go?
The application assigns connections to a pole group as they are created. So that algorithm is kind of up to all of you. Today it's round robin, so it's just going to assign them to the next one. And this is done up in the SPDK target application, not in the library. The library just says, here's a connection, please assign it to a pole group. Right? And then the example application happens to use round robin to do that. I don't think round robin is the best choice. Probably something based on load balancing would be better. And I suspect, depending on how you want to code up your target or what you're doing in your specific environment, there might be further optimizations around NUMA or something like that.
So, okay, we got a question over here. We have one, maybe two left at us.
So I'm wondering, if in the future you support SPA over the TCP/IP, so
yeah.
what will be the network overhead and such? So what do you expect the performance will be?
I don't know. I really can't tell you. It depends on how efficient the TCP/IP stack is relative to RDMA. RDMA is offloading a lot to hardware that you have to do in software with TCP/IP. So I think we'll see when it comes.
Hi. So how how do you compare one I/O queue pair per connection versus multi-queue pair per connection? Or what's your advice?
Can you say it again? It was one I/O queue pair per
connection.
Yeah.
Versus multi-I/O queue pair per connection. Like, given a connection, can I create multi-I/O queue pair?
So the backend, the NVMe queue pairs and the NVMe queue pairs are not related necessarily to one another. The NVMe queue pairs are a connection by definition in the spec. So like an NVMe queue pair is an RDMA queue pair.
Yeah,
that I can't change. But the mapping back to an NVMe queue pair behind the scenes, there will be one NVMe queue pair per thread. And so all of the connections you assign to a pole group, when they route I/O to the same namespace, which is an NVMe device, will use the same NVMe queue pair.
So maybe I need to go read stuff. But I don't see with this model how I determine the number of poll groups to organize things into. What makes me choose more than one poll group? What makes me choose 10 poll groups?
Well, you can only use a poll group from each poll group from the thread it was created on. So if you want more than one thread, you do one per thread.
Is there any reason to ever do more than one per thread?
I don't think with today's design there is, but I think as we make it possible to later move poll groups around, if we can find a way to do that, then I think you might want to be more granular than one per thread so that you can shift work around. But it's not possible to move them today.
Thank you.
It's is it working? Try again.
Can you hear me now?
Yeah.
Okay. This is actually an answer to somebody who asked the performance of TCP transport instead of RDMA over NVMe. My company is working on it right now, and it's few percent worse than RDMA. By few percent, I don't have the exact number, but it's less than 10% worse. I believe it's between 5 and 8%.
All right, I think that's
Yeah,
That's
I'm
it.
over.
okay. Thanks, Ben.
Yep, thanks.
Well done.